In this video, we're going to look at a particular concept called the root mean square velocity. The root mean square velocity is a method for us to calculate, on average, the speed that gas molecules are traveling in a container of a particular kind of gas. Now, you could calculate the average velocity by doing this particular kind of equation that you see here, and essentially that's the square root of the average of the squares of the individual velocities of each particle of that gas in a container divided by the total number. So that's the average. That's how you calculate the average, the square root of the average. Well, we just don't have a way to be able to do that. You cannot look at each individual molecule and measure their velocities all in a snapshot to be able to calculate their root mean square velocity. And so, because you have so many gases going at so many different velocities, in fact, you've got this kind of bell curvy looking distribution, we have to find out a different way to do that. And it turns out that we actually have a way to relate velocity to kinetic energy. And it turns out kinetic energy is equal to 1/2 times the mass times the velocity squared. And then previously we had talked about kinetic energy in the kinetic molecular theory, where it was directly proportional to temperature. And it turns out that we can write an equation that says that kinetic energy equals to 3/2 times the universal gas constant times temperature. And so that gives us a relationship between gases at a particular temperature, kinetic energy, and then we have kinetic energy related to velocity. Aha. So if we know that 1/2 times mass times velocity squared equals kinetic energy, and 3/2 times RT equals kinetic energy, then we should therefore be able to set these equal to one another. And so let's do that. So we're going to set them equal to one another. And what we're going to try to do is solve this equation now for velocity. All right. So we solve for mu, or velocity. And when we do this, this gives us an equation that's called the square root of 3 times RT divided by little italicized m that I have written here. And what this is molar mass, the mass of that molecule, but in the units of kilograms per mole. So this is pretty specific. I don't really know of another situation in which we're going to change the molar mass into different units. And so this is why I'm going to write the little m in a weird italicized way. And at the R here, we're going to use a different R than what we have previously been using with the other ideal gas laws and combined gas laws. And it's going to look kind of the same, but the unit's going to look a little different. So the value is 8.314. But instead of liters times kilopascals divided by moles Kelvin, we're going to give it the units, or rearrange the units of kilograms meters squared per second squared Kelvin. And so this is a different unit used for the R, universal gas constant R, but it ends up giving us the same value of 8.314. And so this will be the only time that you use this particular R gas constant. So there's some additional things that I wanted to talk about when it comes to the velocities of gases. One thing that here on the left-hand side that you can see with this graph is the number of molecules or fractions of molecules on the y-axis, and the velocity is on the x-axis. If you take a single gas and then you look at the distribution of gases and their velocities within that particular temperature, then you can determine that the higher the temperature. So if you look here, you have 100 Kelvin all the way up to 1,000 Kelvin. So you're going up in temperature, you're increasing T. The distribution of the velocities flattens out. So the curve will flatten. When the temperature is closer to zero, the distribution kind of spikes, and you tend to have more molecules closer to that apex within that equation than not. The other piece of information that I wanted you to look at is relative velocities of different gases to one another. So this is an or y-axis, the fraction of molecules or number of molecules. X-axis is the velocity. And what you can tell is at the same, so we're assuming we're at the same temperature here, that whenever you're looking at gases, say like helium versus neon, argon, krypton, and xenon, the molecular velocity is directly related to the mass, so the molecule velocity is directly related to the mass. The lighter the molecules, the more fast they move than heavier molecules. So lighter molecules move faster than heavier molecules. And so you'll see that along with that average faster movement, you'll also see a greater flattening of that curve compared to slower, heavier molecules as well. So let's use all this information to help us calculate the average velocity or root mean square velocity of a gas. So with this particular problem, it says calculate the root mean square velocity of oxygen, or O2, at 20 degrees Celsius. So here's our equation. The root mean square velocity is equal to the square root of 3RT over the molar mass in kilograms of that particular substance. And so let's just make sure that we have T and our molar mass in kilograms as the appropriate units, and we already know R to be our 8.314 kilograms meters squared per second squared Kelvin. And so how do we know what our molar mass is? Well, we have our formula O2. So we know oxygen has a molar mass of 32.00 grams per mole. But let's convert that to kilograms. So we know for every 1,000 grams, it's equal to 1 kilogram. And so that will give us essentially a value of 0.03200 kilograms per mole. And so that'll be our molar mass in kilograms per mole. And our temperature is 20 degrees Celsius, but remember we do everything in Kelvin, so we're going to make that to 93 Kelvin. So all we have to do is plug these values in. We have square root of 3 times 8.314 kilogram meters squared per second squared Kelvin times the temperature, 293 Kelvin, and we're going to divide that by the molar mass of 0.3, 0.03200 kilograms per mole. Okay, and so what we want to do here is go ahead and let's cancel our units out, if you will. And so let's go ahead and cancel out our Kelvin, and then our kilograms are going to cancel. And if you'll notice, I'm putting moles in here. Essentially, we're going to kind of set that to the side and note that when we calculate everything, all of the velocity that we're going to get here is the velocity per mole of that substance that we're looking at. Okay, and so we can kind of just set that to the side, and that will leave us with the units of meters squared per second squared. And so when we take the square root of that, that'll be meters per second, velocity per mole. Okay, so the square root of this particular substance, so we'll take 3 times 8.314 times 2.93 divided by 0.03200, and we'll take the square root of that, gives me an answer of, which is in 3 sig figs, let's go 3 sig figs, 478 meters, sorry, not meters squared, but meters per second. and this is per mole of O2. All right, so this is how you use the root mean square velocity equation and how you solve for that of a particular substance at a particular temperature.